Ska vi kalla det för den akademiska minuten som har gått nu då, så får vi väl köra igång om folk har scheman att förhålla sig till. Så att jag hälsar väl allihopa god morgon och välkomna till oss på DF Kompetens. Jag heter Max Lönnqvist och jobbar som Key Account här på DFK, som vi kallar oss själva i enklare lag. Vi ska snart få höra på morgonens föreläsare som är Barry O'Reilly, som många säkert känner till sedan tidigare. Men vi börjar med lite praktiska grejer. Och det är ingenting som är så dramatiskt, men att vi försöker hålla oss mutade under själva föreläsningens gång. Frågor får man gärna ställa i chatten as it goes, alltså under föreläsningens gång. Barry kommer att se frågorna och sen kommer han besvara dem i tur och ordning när det ges tillfälle för det. Vill man hellre ställa sin fråga så att säga live, så går det också bra att göra. Och då ställer man, vi talar om så att säga när det börjar, när man faktiskt kan ställa frågan live öppet så här över Zoomen. Så om man hellre vill göra det så talar vi om när det är läge för det. Vi tänker hålla på ungefär till 10.00 i tanken. Så ja, där kring. Morgonens frukostseminarie handlar i stort om hur man samtidigt lär sig arkitektur och molnet. Hur man kan kombinera de två som ett lärmoment. Och det går då under namnet An Introduction to Residuality Theory. Och med de orden så lämnar jag över till Barry. Varmt välkommen till oss.
Tack Max. Så jag kan lägga till att när du ställer frågor i chatten att det går att ställa frågor både på svenska och engelska. Men nu går vi över till engelska för att det här är alldeles för jobbigt att ta på svenska. Och att vi har några internationella gäster på sessionen. So, switch to English. Welcome everyone. This session is called An Introduction to Residuality Theory. We're going to look at a new way of looking at the entire concept of IT architecture, which is going to turn a lot of things on its head, a completely different way to think about the design of software systems, and something that will help us in our journey to learn both how do we build systems, how do we design systems, and how do we cope with this monstrous thing called cloud, which for a lot of organizations and for a lot of architects is very, very difficult. So let's get started. So first, for those of you who don't know who I am the founder of a little company called Black Tulip Technology, which is based here in Stockholm, out in the archipelago. And Black Tulip Technology is almost exactly 3 years old, and it was founded with the goal of changing the concept of IT architecture and making IT architecture relevant to the modern world that we live in, because it really hasn't been moving very quickly over the last 20 years. I'm a PhD candidate in the subject of complexity science and software engineering, and the mission of Black Tulip is very much to present software architecture as the meeting point between the complexity sciences, which say that we can't know anything about the world that we live in, and systems engineering, which says that we must know everything about the world that we live in order to be able to control it. And these two conflicting points are really what causes us as architects, as designers of systems, a great deal of pain, because we're expected to be in control all the time when we work in environments, in complex human and social environments, where we're absolutely, definitely not in control all the time. And so these two things cause us a great deal of pain and are very, very difficult to address. And we're right at the edge of what Western science can do for us in those terms. In previous lives, I've been a startup CTO, I've been an architect for 20 years. I've been chief architect at Microsoft Consulting on the Western Europe level. I'm the global lead at Microsoft so for the solutions architecture community. And in those roles back, I think 7 years ago in 2014, I was given the task of making architects. How do we make architects who can cope in this new world of cloud, where the demands on them are perhaps a little bit tougher than they were before? And so the question that we're trying to answer, what we're going to talk about today is cloud architecture. So what is cloud architecture, and is it, or why is it different than what we call system or IT architecture that's gone before? And a lot of architects out there feel very, very nervous about cloud. A lot of people are feeling kind of angst or stress because they feel left behind. There's a lot happening. Cloud is very, very big, and for a lot of people, very, very scary. Cloud is if you think about something like Microsoft Azure, Azure is 1,600 products. 1,600. And if you think about how we've done architecture in the past, as an architect, if you're working as a consultant or working at a company, you might be responsible for one platform or one technology, and you could call yourself a SharePoint architect or a BizTalk architect or a WebSphere architect or an SAP architect, which was big enough in its own right. And you worked with a product that was released every third year, and you had a year's warning about what features were coming in the new release. And the things were pretty straightforward. You knew you were the expert in your platform, and you knew how to make decisions about that platform based on your expertise, based on the fact that you knew every API, that you knew everything that could happen in every way that you could configure that system. And you worked with one, maybe two, maybe three. If you had a breadth of experience, maybe 3 platforms. And suddenly you're working with something like cloud, and you've got 1,600 products. And they're not released every third year. They're released every 4 to 6 weeks. They're changing. So how do you keep up with that as an architect? And it's not just the technology that's changing, but the ideas around how we should build, architect, and manage and deliver systems are changing constantly. And so you've got this flood of ideas, things like DevOps, things like containers, things like serverless. Things like event sourcing. These ideas are coming so thick and fast that a lot of architects, a lot of people feel very, very overwhelmed by what's happening. On top of all that, the world that we live in has become much, much more complex. And so businesses are getting used to the idea of living in a state of constant flux and constant change, which means that the business environments that we work in are no longer stable. It's becoming more and more common for companies to globalize very, very quickly, even when they're small, which means that you've got to manage many, many markets, many, many considerations. And so there's a constant tempo of change, both on the business and the technology level. And at the same time, technology is maturing. And we're expected as architects to deliver in a way that we never delivered in the past. Back in the 1990s and the early 2000s, it was perfectly acceptable to deliver a software solution that did something and tell the business, this is what it does, this is how it works. It's limited, so your business has to work around it. That doesn't cut it anymore. Businesses expect software to be responsive to their needs. And so they're going to tell us as architects, this is the way the business has to work. This is the rate of change. You're going to have to build software that can cope. And this leads to a very, very difficult situation for a great deal of software architects. And we have to ask ourselves the question, how do I keep up with this? How do I keep up with architecting in the cloud? And the way many of us are used to learning these kind of things is, if you want to learn something technically, you go to the API level and you try to have the same level of knowledge as developers. And if you try to do that over 1,600 products with a release cadence of 4 to 6 weeks, you're going to get burnt out very, very quickly. Another way to do it that architects have done in the past is to abstract away all the technology details and only work with the business and process abstractions. In a world of constant change, business and process abstractions are being called out very, very quickly. And the concept of the enterprise architect or the enterprise repository, which is a big basket full of mapped out processes and things, is very, very quickly being questioned. And I know some of you might work at quite large companies and that hasn't reached you yet. But the concept of process mapping is under question. And so we have to ask ourselves, if we can't reach technical expertise because there's too much going on, and we can't carry out work in the old way, in the old style of doing enterprise architecture, then what can we contribute as architects? And what do we have to learn? And how do we prepare ourselves for this world of constant change and flux? And so one of the things we have to realize first and foremost is, what is cloud? What is it that we're talking about when we talk about cloud? And the first thing that we have to realize is that we're not going to accept these simplistic descriptions of what cloud actually is. So it's not hosting, it's not someone else's computer in the sky somewhere. It's not simply a data center moved to somewhere else. And it's not an evil plan by Microsoft or Amazon to take over the world. It's not a business model. So a lot of people talk about cloud as if it was just a web host. A lot of people talk about cloud as if it's a business model from the Microsoft or the Amazon perspective. But what cloud actually is, if you're an architect, the way to see cloud is that it's an entirely new architecture. It's an entirely new way of building software systems with an entirely new set of paradigms and ideas about how components should live their lives, how they should be commissioned, how they should be deployed, how they should be managed, how they should be programmed. And what cloud actually is service orientation, which is an old idea, which has been somewhat discredited, but a very, very solid idea theoretically. It's service orientation applied across the board. So you apply service orientation to hardware, what you get is services that commission servers and manage those servers. It's applied to the network, so you can, through the calling of software services, build and create and configure networks. And to software components, through calls over a service-oriented interface, you can build, program, manage, deploy, take away software components. And also software packages can be managed through software interfaces. So cloud is really the delivery of what was promised way back in the early 2000s when we talked about service-oriented architecture. Cloud is the natural extension of those ideas. And so then to the next question, then, what is cloud architecture? Well, cloud architecture is learning how to work with these ideas, understanding what's changed, what's different from the old days of N-tier architecture and best practices and architecture by spreadsheet or architecture by principle. And what is it that we have to do? What is it that we have to do differently? And so becoming a cloud architect is actually very, very difficult. There's a couple of different groups of people, and we probably have all of these groups represented in today's audience. Firstly, there are software developers among you. And the software developers will be looking at the old style architects, and they honestly will be thinking, we don't want to do that. This is boring. This stuff doesn't work. We don't want to be the people who turn up in meetings and draw lines in boxes. Software architects with a little bit more experience who understand the importance of those lines and boxes will be feeling intimidated. There's too much technology, there's too much going on, things are moving too quickly, it's hard to remain credible, and it's hard to establish credibility with those senior developers who know the technology, but maybe haven't had any formal training as architects. And the problem is that the formal training that we can offer them as architects isn't relevant anymore if they're working in the cloud. So becoming a cloud architect is hard. How do we navigate that path? How do you become an architect, and how do you confidently build solutions in the cloud? And if we look around for solutions to this, you'll find that the vendors are very quick to tell you that this is how you become a cloud architect. You take our certification, you learn about our tools. The problem is that those certifications are really just a little badge you get for being able to recite a vendor's marketing. And they're about what the vendor wants to tell you about their platform. It's not about becoming an effective architect and making good decisions for your business. Old style architecture, things like TOGAF, things like Zachman, things like enterprise design patterns and things like that, they don't work. They don't work in this environment. And so what we need to do is that we need to be able to think differently, and we need to take a step back. What is architecture? What's it for? What is architecture in the context of cloud? We need to learn differently, obviously, with this flood of ideas and components and structures and different ideas. We need a different, more effective way of learning. And one of the things that a whole bunch of people, and even people at Microsoft, have struggled with when it comes to cloud, is that for a very, very long time, our industry operated very comfortably in silos, and we had infrastructure people, and we had security people, and we had developers, and we all worked in our own little offices, and we threw stuff over the wall to each other, and we didn't like each other, and we complained about the other group. And one of the things that you'll find as an architect thrown into these cloud projects is that all of a sudden you're doing infrastructure, you're doing security, you're doing development, you're not quite sure where one starts and the other ends. And that's one of the most confusing things about cloud development, and it's one of the most terrifying things. So part of my job at Microsoft a few years ago was to make sure that our architects passed their certification. And I had a whole bunch of infrastructure architects terrified of the code, and I had a whole bunch of developers terrified of concepts like subnetting and simple things like ports and networking. And so this kind of architecture requires a breadth from its practitioners that maybe wasn't required before. There's also a huge amount of uncertainty. And this is key. The uncertainty in the way we work is really tough, a really tough problem. We have domain uncertainty because modern business is a very uncertain environment with a lot of moving parts, and things change very, very quickly. And that's thanks to globalization and e-commerce. There's uncertainty in the technology. Products appear and disappear among these 1,600 products that exist in a cloud platform. There's huge uncertainty around process as well. The agile revolution is right now being questioned. We're looking at the old ways, we're looking at the new ways, and we're saying none of this actually works. So what is the right process? How do we deliver software? And how do we make decisions about that process? So there's uncertainty everywhere. And that's something we're going to come back to. And so one of the things that's difficult if you're a senior developer right now in the world is that you're expected to learn cloud and you're expected to learn architecture at the same time. And that's quite a task for your organization's training budget. And so how do we learn both of these things at the same time? There's no point in learning old school architecture on a course, the old school MBA style architecture, when it won't be applicable to cloud. Then when you go and learn cloud, you learn about a bunch of products, but you don't learn how to architect and how to think like an architect. And so the mission that we have here, what we're trying to do is to create cloud architects quickly. And we have to give those architects a good base in modern software architecture, and that's modern software architecture. And we need to give new relevant tools. And what we want to do is redefine architecture as a science of uncertainty. And so uncertainty, as I've looked at this problem over the last 5 or 6 years, uncertainty is the key issue that first of all creates the need for architects. If there was no uncertainty, there wouldn't be any need for us. Then we would just choose a product and put it into production. But also the word science is incredibly important because we've become trained as an industry to think that rigor is a book with a pretty animal on the front and absolutely no peer review, and people writing about ideas, evangelizing ideas, and taking no responsibility for the veracity or the rigor behind those ideas. And so we need to take a step back towards a more scientific way of thinking. And so a couple of years ago, I launched the idea of anti-fragile systems design, which was a set of heuristics that I built up over a number of years. And these are the tools I used at Microsoft and at other companies to lift architects, to get them to understand that the world around them was very, very different than what they learned in university. And that cloud was changing things. And so this was a set of simple heuristics for people who were working in complex environments, and it was incredibly popular. And so the videos and the podcasts and the articles have been seen by tens of thousands of architects across the world. And so these ideas really caught on very quickly, and it's been very, very successful for me and for those who've engaged with it. And so I had a choice to make here. The choice was to do that thing with the pretty animal on the book and go on a speaking tour and do the same thing as every IT guru in the last 25 years. I chose a slightly different path, and I went back to university. And I said I want to expose these ideas to scientific rigor and criticism, because we have to make sure that this stuff actually has a solid ground to rest on. And the results of that have been very, very interesting. And the result of that is something called residuality theory. And residuality theory is a theory of architecture that helps us to explain what works, what doesn't work, and what things are relevant in the context of a certain problem. And I've published a couple of papers that you can see here on the academic level. The feedback on these is that they're very, very tough, very, very hard to understand, because they dig into concepts like the philosophy of science and probability theory. And so I've produced a couple of softer articles in a business journal called Cutter in the United States that talks about the same ideas at a slightly less academic level. And so what residuality theory is actually doing is providing a means for architects to understand their profession. And we'll have a look at what that means in a minute. And so it's a scientific ground. And so it allows us to assess and assimilate and understand different frameworks and tools and technologies very, very quickly. And it's a base set of assumptions that we should rally around as architects so that our work is more professional. And this is very much about being peer-reviewed and scientifically verified. And so one of the things that my research has led me to ask, which is incredibly important, is what is the philosophy of architecture? What does that mean? Well, very few of us are able to answer that question. In fact, our entire profession struggles to answer this question. What is the philosophy of architecture? If you ask a doctor, a medical doctor, what's the philosophy of medicine, they'll be able to tell you. They know very quickly what the philosophy of medicine is, and it's all based upon a bunch of principles, things like don't kill people, first do no harm, things like that. And the philosophy of architecture, as you dig deeper into it, there very few architects are able to even have a discussion about this, because our work, our view of the world, our understanding of the reality that we work in is almost entirely accidental, and we've inherited it from a bunch of people, among them von Neumann, Turing, some ideas from the 1940s, something called cybernetics, which we won't go into today, where we make assumptions about the world around us. And so what I've discovered is that architecture actually doesn't have a philosophical structure. It doesn't have an understanding of who or what it is. And so what we've done is we've just simply borrowed ideas from other people, from cybernetics, unfortunately for us, from MBA type thinking about business. Our philosophy is entirely accidental. And so it's time to take a step back and ask, who are we? What are we? Why do we think the way we think? And what do we need to do in order to understand that? And so this is what our philosophy leads us to when we take these ideas about cybernetics and a few other things like essentialism and structuralism, which permeate our thinking as architects almost accidentally. And there's very few architects who know what those words mean, but they define how you deliver your solutions. And so what is architecture? You can see in this diagram here what we think architecture is. Architecture is a socio-technical context. It's a business doing something. And we're talking about enterprise architecture here, not the architecture of software on chips. And so on a higher level, we say that a business has these things, which are capabilities. And that a business can be broken down into a set of capabilities, and each capability can be broken down into a set of processes, and each of those processes then is taken care of by a number of software components, which we have down here at the bottom. And this is the philosophy of architecture. This reveals a lot about how we think about the world. We say that organizations are machines, and they can be broken down into these smaller parts, and these smaller parts can be studied and managed and governed and mastered. And that is the philosophy of architecture. Reality looks like this. We have a person, this blue person here, and this person wants to achieve something. And that person is surrounded by a society, by a whole bunch of different things, people and software components and groups of people and organizations and things like that. And in order to achieve whatever it is that this person wants to achieve, we observe the system and we ask, what are your requirements? What is it that you want to achieve? That's how we do architecture. And what we do is we see these links between this person who wants to achieve something and different groups, different organizations, different software components. And we see these white arrows. And these white arrows form the basis for this, all of this over here. And these white arrows are what we see as structure. And we impose that white arrow structure on the organization. And we say, this is how things work. These are the processes. And when we read the literature on complexity science, we realize that there's a whole bunch of other stuff going on. You see these green arrows. These green arrows are links, interconnectivity between actors in this network of people and software components that we can never see and never understand. And sometimes these connections are people who know each other. Sometimes it's people having coffee. Sometimes it's a social interaction where the two people actually don't even know each other, but what they say and do in the public sphere influence each other. These green arrows are impossible for us as architects to map. But it turns out that they have massive, massive influence over these white arrows, and they cause these white arrows to bend and shape over time. And this makes it possible for new actors to pop up. And all of a sudden you get these red arrows, which are always a surprise to all the people over here. These red arrows are a direct result of these unseen green arrows. And suddenly there's a new way to do something. And as architects, we call this disruption and we call this change, and we mostly ignore it. But the problem that we have is that by focusing on this picture of architecture over here, this rigid structural picture of human organizations, we consistently miss the red arrows. We consistently miss the impact that they're going to have. And those red arrows can turn up at any stage. They can turn up during a project, they can turn up in production, they can turn up during the design phase. And this problem is what's led to the development of agile software development, because agile said that this old way of doing things, this rigid architectural way of thinking about doing things, can't see the red arrows. But agile can't see them either. And agile isn't actually that far away from classical architecture, even though they think they're radically different. And they can't see the green arrows either. And so they don't even know. It's one thing to be able to react to things, but they don't even know what they're building into the architectures that they're building. And so we call this this imposition of structure over this complex dynamism that exists in social ecosystems. We call this the component metaphor. The component metaphor is the belief that organizations, something as complex and intricate as an organization of human beings acting in a market, which is incredibly complex, incredibly unpredictable, and incredibly random, can be mapped as a bunch of processes and software components. We call this the component metaphor. And the component metaphor is our philosophy. It's the philosophy of architecture. We believe that by talking to people, by asking them what they want, that they understand what they want, that they can express what they want, and that expression can be boiled down to a bunch of processes and components. And that's been a major mistake of software architecture over the last 40 years, because this reality simply does not exist. It allows us to be busy. It allows us to pretend that we've got the answers. It allows us to produce something that looks and feels scientifically credible, but we work in an industry with an 83% failure rate. So something is very, very wrong. And this is it. It's our grounding philosophy. It's not about finely polishing this, because you can't put lipstick on a pig. This has to go. This way of thinking, this way of viewing reality is the reason that we find architecture and it's so difficult, and it's the reason that cloud architecture is failing. And so we have to ask the question, is software architecture ready for cloud? So the practices that we engage in today that we call software architecture, which is mapping processes, mapping capabilities, making decisions about components based on that, asking users and business sponsors, what are your requirements? Are these purposes fit for purpose? And they're not. The way that we do architecture today is we've absorbed this philosophy, which is like MBA light. So an architect becomes like a mini management consultant, and this approach tends to alienate developers, and developers don't get it. They don't like it. And what I've seen at company after company, as cloud rolls in, developers become more independent and they start to shut the architecture function out. They don't want architecture in the room anymore because it slows things down, because it cares about a structure that obviously doesn't exist. A lot of architecture is considered by developers to be terribly boring, and they might be right about that. And it tends to be focused on old silos, on internal IT department politics, with command and control at the center. And one of the things that you'll discover very quickly if you start to dig into system complexity and dynamic systems is that command and control does not work in a complex system. But enterprise architecture is still very much concerned with command and control ideas, which belong very much in the past. And so we have some issues with how we do architecture. One of the problems we have is with design. Design involves predicting the future. When you make a design decision, you're saying, this is going to hold. This is going to hold for a future. The problem is with those green arrows and those eventual red arrows, we as architects and nobody can actually predict the future. It's beyond the grasp of Western science to predict the future in these complex socio-technical systems. They tend to be based on requirements, and requirements is a way that architects get away from the problem of predicting the future, and we go to the business and we put the onus on the business. We say, I'd like you to predict the future. And that's simply a way of bullying the business into taking responsibility for the fact that none of us are able to see the future, so that we can work in peace, deliver code that doesn't actually work, and get paid for it. And so design is very much about quickly identifying these capabilities, these processes, identifying components as quickly as possible. It uses very fast abstractions. We try to use patterns as if every enterprise was exactly the same as every other enterprise, which is another philosophical assumption that gets us into trouble. And so design has become neglected. It's been neglected by the agile community, who've seen the futility of trying to design everything up front using the component metaphor. So we've got two choices. You can use the component metaphor and get everything wrong, or you can use agile and ignore the fact that you're getting everything wrong and just live in a state of chaos. Actually, it turns out there's another way, and this article talks about how we can rethink design. Another problem that we have as architects is the ability to manage risk. And we tend to, in the first instance, focus on project risk. And so we're very focused within it. And this is because of IT department politics and budgets. We're focused on project risk, time, schedule, and budget. And so risk management tends to be very, very siloed. So the financial department do financial risk, the project does project risk, the architect really should be doing technical risk, but we miss that a lot. When we do risk management, and we've all done this, you do the whole traffic light thing, or you assign probabilities to risk, We can't actually do that. We can't predict the future of the systems that we're working in, and that's a huge problem. And we'll look at that more in a minute. And so enterprise risk management is essentially more about a nice feeling of comfort, saying we've handled the risks when really we haven't done that. And there's another article you can read on this, on how risk management is something that actually is a very, very intense design activity that we need to pay more attention to. And so where we are right now is that we're moving into a world where cloud is going to be the dominant architectural paradigm. And it's going to be that for a good while. And we need to architect cloud solutions. And we have a bit of a problem then, because what we've said in the last few slides is that requirements is broken. Risk management is broken, design is broken. We've lost engineering. Engineering believes in cults, right? If you try to find your engineer to talk to them about architecture, they're in some kind of stand-up meeting, or they're sticking post-it notes on the wall, or producing some mystical thing called a backlog, which solves very, very little. We've lost engineering, and we've lost that thread, we've lost that conversation. The tools and the thinking around software architecture are exactly the same as they were 20 years ago, with planning and control at the center and this concept of governance driving everything. We need something else for cloud, and we need something else for the modern world. And if you're a chemical engineer, then you have a scientific base on which your work is based, and the philosophy is decided for you, and that's called chemistry. If you're a mechanical engineer, then you have a philosophy and a natural science behind you, and that's called physics. If you're a programmer, you have a science behind what you do, and a philosophy behind what you do, and that's called computer science. And computer science does, to some degree, influence architecture. Architecture doesn't have anything, and that's the problem. We've ended up with a mismatched bag of stuff that we've just grabbed from different shelves without really understanding what it is. And it's not that anyone's done anything wrong in that journey. It's just that we're very, very young. Our entire industry is only 60 years old. That's why we're in the state we're in, not because we're stupid or because we've chosen the wrong things. It's a natural human progression. What we're trying to do is to establish something, and that something is residuality theory, which is going to form the scientific basis for architecture. And residuality theory, in turn, is based on complexity theory and systems engineering. And again, it's about marrying these two things that contradict each other. And residuality theory, and now we're getting to the point of the talk, residuality theory says that systems in complex environments cannot be modeled as processes and components. If we continue to model things as processes and components, then we're going to continue to see these huge IT project failures. We're going to continue to see an 83% failure rate in our industry, and we're going to continue to see architects being shut out of the conversation, because what we're saying about processes and capabilities just isn't relevant to what's actually happening in everyday business and everyday software development. So instead of describing things as processes and components, what we're going to do is we're going to describe systems as a stack of residues. And a residue is a view of the system under a particular form of stress. And so a residue is essentially a set, and it consists of people, it consists of software components, software functions, and it consists of flows of information between those software functions and people and each other. And so the way it works is this. Whenever I describe a problem to any of you who are software developers or software architects who are on the call, you will immediately think of a solution. You'll immediately think, this is how we solve this problem. And we call this the naive architecture. And we all do this, and there's no point in trying to pretend that we don't. But the minute that you hear a problem, you start designing it. You start thinking, what kind of components are involved here? How do we use them? And what should they do? And the way a residue works is that we imagine a form of stress on the system. And that form of stress can be anything. What stresses this system? It can be anything from a competitor drops their price, the development team quits, a competitor does something different, the technology vendor changes how the system works, there's a fire, the data center fails, or ridiculous things like giant fire-breathing lizards attack your city. A stressor is anything that impacts the way that this system is going to behave. And we ask ourselves, is this naive architecture good enough? Is it good enough for our system? And generally it's not. And so when we imagine our system in this kind of stress, generally we have to change it. And so the residue, the bits of the system that are left over after the stressor hits the system, change, and we change the system so that the residue is bigger. And what we're saying is that this new architecture that we've come up with here, these changes that we've made over here, there will be better placed to survive this particular form of stress. And we do this in a way that costs as little as possible. And so what we do then is we take our architecture and we start thinking about different forms of stress, and we apply those different forms of stress to the naive architecture. And so what we end up doing is developing a picture of a whole bunch of different residues. And these interconnected linked residues describe our architecture. And so all of these things, all of these boundaries here that you see, represent connections between these different residues. And this is a completely different way of modeling a software system. All we have is people, software functions, which is a simple bit of code that executes, and flows of information between them. And information will flow and stress will flow across the boundaries of these residues and impact each other. And this is an entirely new way of modeling a software system. And it turns out that there are mathematical models that can help us to model systems like this, and this is what my research is based on, which will eventually lead to computer support for managing these kinds of architectures. The next thing we have to do then is that we can't afford to build every single residue. So what we start to do is we start to compress the system. We start to make the footprint of the entire system as small as possible by integrating these residues. And so what we've done is we've changed the process of design from going from requirements to identifying capabilities to processes to software components. And what we've done is we've identified sources of stress, we've identified residues, we've identified the boundaries around those residues, and what we've done is we've broken down those boundaries in order to make the system smaller while still preserving its ability to cope with stress. And this has some very, very interesting implications for how we build systems in conditions of high uncertainty. And so these ideas build upon complexity science, and in the course that we're presenting with DFK here in Sweden, we dig deep into things like this guy here, which is the Cynefin framework, which helps us to understand the complexity in the world around us. But these ideas aren't just some pie in the sky IT thing that's made up in order to be pretty in a PowerPoint. This is real science that we're dealing with here. One of the things that's really, really important in these ideas is that we're talking about the concept of fat tail distributions. And so if you are educated in STEM at a Western university, you tend to come out of your education believing in this thing here, which is a normal distribution. And if we talk about the kinds of failure that happen in an IT system, generally we tend to focus here in the middle of the bell curve, and we say in here we've got things like network failure and disk failure and software bugs and all those predictable things. And the way that we solve these problems is very obvious. It's something called systems engineering, and systems engineering has existed for a very long time. It's a mature field. And generally, we don't use it anymore in the software industry, which is why things are so terrible. So that's one of the things that we have to fix. But even if we got better at systems engineering, which we absolutely definitely need to do, and which the course will focus on a lot, we have these problems out here in what we call the tail. And the problem with the tail is that enterprise risk management ignores the tail, because everything that has a low probability, which anything in the tail has, falls to the bottom of the list, and we don't deal with that. And the problem that we have to solve unfortunately looks like this, because normal distributions don't exist in the real world. What we have instead are power law distributions, or fat tail distributions. And that means that the tail of what we're working with is much, 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 much bigger than a normal distribution. And that means we cannot ignore the tail in the way that enterprise risk management ignores the tail. It means that the area under the curve here is so big that these things are going to constantly be hitting your system. And the lesson that we have to learn from probability theory is that we just simply cannot predict the future of these systems. In order to be able to survive as architects in the modern world, we're going to have to build and deliver systems that can cope with stress that they haven't been designed to cope with. And that stress can be a pandemic or a ship getting stuck in the Suez Canal, but we're not going to be able to predict what's going to happen, and the system's going to be expected to cope whenever that happens. How do we solve those problems? Another very important idea that's introduced in these is the idea of hyperliminal systems. And the systems that we build as software engineers are hyperliminal. What does that mean? Well, the systems that we build as software engineers, they look like this. They're here in the middle of the diagram. They're ordered and they're structured. Okay, software systems, even though you might laugh and think that your developers don't build ordered, structured systems, computer systems are ordered and structured. They're based on mathematics. They're predictable. Okay, we can predict what's going to happen in a computer system. They are not complex. They're actually quite simple. They're dumb machines. They do what we tell them. And so the kind of things that you do when you're building ordered, structured systems are well understood. And when you have an ordered, structured system, it's possible to have things like best practices. It's possible to have ideas and patterns that you use over and over again. And we've adopted a lot of that thought in our work as software engineers. And that works. It works really well if you're engineering something like an airplane or a car. The problem with software is that we take these ordered systems and we force them to live in this space here, in a disordered space, which is human systems. So software systems have to exist in a human system, an organization, and a market, which is inherently unpredictable, which is fat-tailed. There's no normal distributions here. There's no best practices. There's no order. There's no guarantees. There's no predictability. And as soon as we build our beautiful, ordered, best practice, pattern-based software system, we put it into this environment. And these arrows here represent the stress that environment starts to put on our beautiful, ordered, structured system. And that what happens is then that the system starts to buckle and break. And the decisions that we make about the order of that system can actually bleed out into the human space and start to control the humans. That means that the software system can limit your ability to do what you want to do, which is exactly what happened when Blockbuster were facing Netflix. Their software system, because it was so rigid, couldn't cope with the stress that Netflix caused, and actually restrained the actions of Blockbuster's board because they couldn't react quickly enough in order to deliver code. So that means that the architect has to spend a lot of time moving between this ordered world and this disordered world. And the way that and that's very, very difficult, right? Because they're completely different ways of working. One has best practices, one has testing, one has structure, and one has randomness and uncertainty. Completely different ways of working. The problem is that what we've done in the past is that we've divided this into two spheres. We've said here we have the technical architects, the software architect or the solutions architect, and out here we have the enterprise architect or the verksamhetsarchitect, as we say in Sweden, or the business architect, and we divided this up. And that just creates silos. And another thing is that when we have things like enterprise architecture or business architecture or verksamhetsarchitecture, we put people who used to be technical into that environment. And what they do is they apply the component metaphor to these random, unstructured human environments where it simply doesn't work. And that's why we're struggling. And so hyperliminality basically means that we're constantly shifting, we're constantly moving. So a liminal space in English, liminal means that you're in transition. So a liminal space is like a bus station or an airport. It's not a place that exists because it has to exist. It's a place that exists because people are in transit, they're moving. And so as architects, we're constantly in the airport, moving between this ordered, structured world and this disordered, unstructured, unpredictable world. And to be able to cope with that, we need a philosophy, and residuality theory gives us that. So residuality theory protects us from a lot of the things that are happening here. So by designing our solutions as residues, rather than components and processes, we're countering our own instincts, and we're forcing ourselves to look at the uncertainty and to look at the unpredictability. And so a major tenet of this way of thinking is the rejection of prediction and control. We cannot predict and control human systems. Now, there's an entire literature, an entire world out there which believes that we can. Or there's a whole bunch of people who want to sell you things that they want you to believe will give you the ability to predict and control. Okay, and then some of it is, sometimes it's an MBA, sometimes it's a really strange set of things called SAFE. Some people think TOGAF does this, but you cannot predict and control the environment around you. And so the key to building these systems in uncertainty is to use stress as the driver of design decisions. As we said, stress is the key thing we do when we decide what are these residues, what do they look like? And this allows us to move away from the idea of requirements or changes in our software, so we don't have to ask the stakeholders in a project, what do you want? What is it that you want to do? Instead, we have a completely different conversation about what is stressing you, what's stressing the system. And so we get a negative view of the picture, or almost reverse of asking for requirements. And it also stops us trying to deal with change or volatility, because we can't predict change or volatility. There's no point in trying to do that. And so what happens then is that we have much more honest conversations with our stakeholders when we say, what will happen in this system if a competitor drops their price? I mean, that should be a basic question that every architect can answer. And I've yet to meet an architect who can actually answer that question. So we capture negative stories about the system, rather than asking people, what do you want? Because the truth is, people don't know what they want, or they don't know what they need, because they can't predict the future either. And we do this without using probability, which means that fire-breathing lizards destroying your city is an equally relevant residue as a network failure. And this allows us to create an emergent picture of the system. And what emerges from this process is a set of processes and components, but it's not the same as sitting down and just drawing them. And they actually emerge from talking about what's going to stress the system. And this radically changes how we think about design. And we design instead by carrying out something called a residual analysis. And all these old school techniques, all these things that we've been doing for years, things like GRASP, things like domain-driven design, all of that stuff disappears, and we get something new, which is residual analysis. And one of the key things that this takes care of, and that was very, very important in the design of residual analysis, is the idea of non-functional requirements. And so as software development becomes easier in the cloud, with things like serverless, and it becomes more isolated, and we're better at protecting ourselves from the actual volatility of software development, the architect is going to be more and more concerned with non-functional requirements as developers focus on quickly producing code. And non-functional requirements at most organizations is a complete and utter nightmare, because it's ignored until the last minute, where people try to make their teams focus on non-functional requirements. It's very, very often an Excel-based checklist. Have you looked at security? Have you looked at capacity? Have you looked at scalability? And very often non-functional requirements are considered too late in a project, and most major project failures, and most of my career has been about rescuing projects from failure. Most major project failures are actually simply a failure of meeting a non-functional requirement, either because it was ignored, or because nobody knew it was there, or because the non-functional requirement was hidden in the green arrows. So we solve the non-functional requirements by working with residuality theory, by working with negative stories, by looking at how different stressors can impact the solution and how it can affect the rest of the solution. And it forces engineering to take non-functional requirements seriously as the first step in design. And so residual analysis then is where we take the idea of residuality theory and apply it to software design. Remember, residuality theory says that a system in a complex environment cannot be modeled as components and processes. Essentially, what residuality theory is saying is that the future is determined not by your agility, not by how clever you are, but by what's left over when your system is exposed to stress, which you can't predict or control. Whatever's left over will determine how well you're going to do in the future, which is why we focus on the concept of a residue being what's left over when the system's exposed to stress. And so there's two major parts to residual analysis. There's a stressor analysis and a contagion analysis. And the stressor analysis is really sense making. This is an alternative to old, tired, dated approaches to requirements engineering. Okay, so this takes away requirements engineering and does something completely different. So we focus on the negative and we ask stories about stress. What happens when a competitor drops their price? What happens when a disk fails? What happens when a new competitor appears in the market? What happens when social attitudes change and shift towards the kind of product that we're building? And so one of the things that architecture has done and done very badly over the last 20 years is that architects, especially older architects, have lectured developers and junior architects about the importance of business and the importance of alignment. And they'll tell you all the time, you need to understand business, but they never tell you why. And so as you dig deeper into residuality theory, what you'll see is the link between the decisions that you make as an architect and actual business reality. And you'll realize that alignment is nothing to do with it. You'll realize that what you're doing is you're building in a complex environment, and that hyperliminal space and the connections between the ordered system and the disordered system are incredibly important. And that means that you really need to understand your organization, and you need to understand the market, and you need to understand the society that you're delivering the thing into. So this isn't about the MBA approach to architecture, which many people have probably tried to sell you over the years. This is about actually understanding your surroundings almost intuitively. So this isn't about learning financial models and trying to impress people with an MBA level knowledge of business. This is about understanding what aspects of the business you need to understand, because it's connected to the decisions you're making as an architect. And so how do we do a stressor analysis? And this is where we start to leave all the theory and the complexity science behind and actually get to heuristics, very, very easy things that we can do in order to better build software systems. So a stressor analysis, we simply make a list of stressors. And they can be anything. Disk failures, giant fire-breathing lizards, war, famine, pandemic, market shifts, changes in attitudes, competitor behavior, the relationships you have with your supplier, supply chain malfunction, anything that causes your system, anyone in your system to be worried. And we make this massive list, and there might be hundreds of things in this list. And what we do then is we divide this list in half, and we take the first half of the list and we do what we said earlier. We create a residue for every stressor, and we look at the stressor and say, what do we need to do in order to survive this stressor? And we build our little structure that we looked at earlier with all of these residues. And as we build, we challenge our assumptions about the system. We challenge the assumptions about what is a process. We thought this was a process, but actually it turns out that if we expose the system to this particular kind of stress, the process becomes dangerous to us. Because if people carry on doing this process under a certain set of circumstances, it's damaging to the business or damaging to our customers. So we take half of the list and we sketch our residues. And each residue then contains software functions, no components, no products, just functions. It contains the people who need to do the work, and it contains the flows of information between those functions and those people and each other. And we don't just do this on our own. It's not the architect. We crowdsource. We ask people, what are you worried about? What could go wrong? We read industry journals. We understand the market, we understand what competitors might be able to do, and we build up this picture of the architecture. And here's an example of what we do and how it might actually work. And this example has a very, very important example of the kind of impact we're going to see. So if we have this is an example of a stressor analysis that's being done for a company who was building and designing car charging stations for electric cars. So a kind of bank of chargers where you drive up along the side of a motorway, kind of like a petrol station, but for electric cars. And the kind of things that can stress this, obviously, new car models, which is stressor number one, stresses this system. And how do we deal with that? Well, we need to have flexible charging connectors, adapters. We need to have extra space and make sure that there's extra ground in case we need to build something completely new, because this is a fairly volatile environment. Things are still changing. Everyone assumes that Tesla are going to be the dominant player, but Volkswagen and Mercedes are making their moves. Things are changing very, very quickly, and we've already seen a proliferation of different standards and things like that. So that's the kind of stressor that allows you to make decisions and change your residue. And already our naive architecture, when I described the problem, you all imagined a charging station with a bank of chargers. Now you're imagining a charging station with a bank of chargers with flexible adapters and a little extra ground that we've bought just in case we need to make quick changes in the future. So the residue is already working. They're already thinking in those terms. The really interesting thing here, though, starts with number three. Number three is that I'm a member of this particular network, and I have a little key fob, little RFID, which I blip with before I charge. And the stressor is, what happens when that doesn't work? What happens when it doesn't work? Suddenly I'm sitting there with an electric car, which maybe has no electricity left in its battery. It can't go anywhere. It's stuck in the thing. I'm an unhappy customer. Nobody else can charge because my car is stuck there. This is a big, big problem, and a real world problem that was observed. And so we increase the residue by adding new stuff. And the new stuff is that we change our process, that we thought we had a process, and say if we built those white arrows, we'd be in trouble. Now, these are the green arrows that we're starting to discover through negative stories. We're going to allow everyone to charge. Process is completely changed. No matter who you are, you're allowed to charge, and we're going to invoice you later when you register. And we're going to use something called ALPR, automatic license plate recognition, to manage this process. So when you drive up, you don't need to log in anymore. You can log in if you're a member, and if it's working. If it's not working and you're not a member, then we'll take a photograph of your license plate. We'll figure out who you are, and if you do it too often, we'll come and visit you. And the next one that's interesting then is stressor number 8 here, which is damage. Damage is obviously something that's going to stress this system, and so people might turn up and damage the chargers because people are like that, or they might drive in. More likely, they're going to drive into them. They're going to reverse into them. These things are going to get damaged because people are driving cars close to them. And so how do we deal with this? We deal with it through redundancy. We need to have more chargers than we might actually need because some of them might be damaged at any particular point in time. And we're also going to put some security cameras in order to discourage vandalism. And the next stressor that's really important is number 12. And this is something that turns out to be a huge problem for anyone in this industry, is that the customer abandons their car in the slot. They turn up, they plug in the car, and when they plug in the charger, and when they plug in the charger, no one else can get it out except them. And they go off and play around at golf, or go shopping, or go and do something else. It takes roughly 25 minutes for a fast charger to get a car to 80%, and you really don't want people sitting around for longer than that. If a particular car blocks a slot for longer than that, it has a massive impact on this company's revenue and also customer satisfaction, and you cannot allow people to do that. And this is where we see residuality theory starting to work really, really well. What we need to do is invoice per minute, and we invoice on a sliding scale, so that if you're there for 25 minutes, it costs a certain amount. If you're there for 30 minutes, every minute starts to cost more. Once you go over 50 minutes, then every minute starts to cost exponentially more, and so it becomes incredibly expensive to leave your car there. for longer than an hour. And we already have something that allows us to do this, which is ALPR. We have your license plate, and we're going to charge you per minute with exponential increase. Well, maybe not exponential, but very, very steep increases in cost to discourage you from doing that. And you see here that one of the residues that we changed back as stressor 3 is suddenly useful in coping with stressor 12. And that's a pattern that you'll see every time you apply this methodology. And if you look down here at stressor number 14, stressor number 14 is icing. Icing is a phenomenon that started to happen in the United States because of their very bizarre political development over there, where two groups of people decided that they don't like each other very much. People who own big diesel and petrol pickup trucks have taken to parking and electric car charging stations just to irritate the people who own electric cars, because they assume that they're of a different political persuasion and that they think they're better than them, and well, a whole bunch of social reasons why they want to mess with people. This is green arrow, red arrow stuff. Okay, the green arrows are things that we never thought about when we were gathering requirements. Green arrows are the resentment between different stratifications in society that have been building up since the 1960s. Those green arrows aren't things we capture in our requirements engineering. The red arrows are people parking their pickup trucks in our charging stations for reasons that seem inexplicable to us. We can't predict human volatility. We can't predict the progress of social systems. So we have to build software systems, business systems that can cope with this. How do we cope with this kind of human volatility in systems that we don't want this to be agile? You can't rebuild a charging station in an agile fashion every time this happens. If you can't predict these things, you don't even know what kind of agility you need. So agile is absolutely not the answer. It turns out we've already solved this problem through a combination of our residues for stressor 12, 3, and 8. 3 gives us ALPR. So if you park your diesel truck, we know who you are already. We have your license plate. Stressor number 8 means there's a security camera making sure that it's you, and we may bring criminal charges against you. And stressor number 12 means that we're still getting paid. And we're getting paid much more the longer you leave your car there than you were before. And so this is something that we see happen over and over and over and over again when we build these systems. It's something which I'm working in my research to mathematically verify will happen every single time. And there is actually mathematical proof behind this. As you work through the stressor list, you're going to struggle to find things that stress your system very, very quickly, because this way of working through residue already gives you, what we're constantly doing is splitting and resplitting and reconfiguring the relationships between software functions and people and the flows between them. And when we do that, this constant splitting and resplitting and recombination, we shift the system to a configuration where the residual footprint, what's left over when it's stressed, is always getting bigger, which means we have more options. When something unexpected happens, it's more than likely that we've already solved that problem. And this is to do with the relationship between infinite sets, and which is stress, and finite sets, which is coupling points in an architecture. So there's a mathematical substance behind this. And so what we're doing as we move through these residual analysis is we're taking these 4 points of manipulation that we have as architects in software systems, which is modularity, weak links, redundancy, and diversity. And there's research behind this from Norway, that these are the 4 points that we can manipulate a system as architects. And when we manipulate these, we make a system more or less resilient. And the problem is that in our industry, because we've adopted the component metaphor, we tend to use patterns to solve these problems. And so we use someone else's patterns. And no enterprise ever has the same patterns, ever has the same stressors. So there's no guarantee that those patterns are going to work. So patterns are a prediction. They're saying that this enterprise is going to have the same problems and the same challenges as every other enterprise in the world, and that's obviously wrong. And so residuality theory helps us evolve our naive architecture to something that actually fits its context, to something that can actually work with the uncertainty that exists in a particular environment. After that, the stressor analysis, we steal some things from machine learning. Like I said, we take our list of stressors and we divide it in half. We use the first half here for design, and we use the second half to test. And what we do is we run a very, very simple test. We take the second half of stressors that the system has never seen before, and we run it against the system at design time, and we say, will the system survive this unknown source of stress? And we run it against the naive architecture, and we say, what percentage of those stressors did the naive architecture survive? And we call that X%. And what percentage of stressors did the residual system survive? And we'll call that Y%. And what we'll see empirically is that Y is always bigger than X. And this is empirical proof that the work we've done in residual analysis actually made this architecture better. And empirical proof that an architecture is better is science. Okay, we've proven something, we've actually done something, which is a lot more than any architectural methodology can do today. What you can then do is you can change the order of the stressors, and you can run this several times, and you'll get several different candidate architectures with several different groupings of components, several different choices made available to you. You can replace some of the groups of the functions with a product, for example. So you can say, we're buying product X because we think it's going to save us money. X is actually a group of functions, and you can use your residual structure to test and say, is this product a good idea? Is it a good idea to group these functions together behind this barrier and introduce a support relationship with another partner? What way will that impact our residue? What way will that impact our ability to respond non-functionally when the behavior of the system changes under stress? And this way you can make much more sensible decisions about what you're going to buy and what you're going to build. And so a whole bunch of architectural tools and ponderings and guesses that we used to make suddenly become structured and have a scientific basis. Once we've done that, then we want to reduce the size of the system, because we can't build every single residue. Eventually that becomes so complicated that we defeat the purpose of the entire thing. So what we want to do is to reduce the space, reduce the size of the solution. And we do this with something called a contagion analysis. And we say, when a stressor hits this residue, does it spread to other residues? Does this stress spread across residue? And if it does, then is it a good idea to integrate those residues? Do we need different barriers between those residues? Do we want to protect them? Is there a way to make this smaller? Essentially what we're saying is, what components can we share? What components can we share across these residues? And the more shared components you have, the cheaper it's going to be to build the system. But the more you share a component, the more you risk contagion, in that one particular form of stress will spread from one part of a system to another and reduce your options in the future. And that's quite dangerous. What we do here is we identify trade-off decisions, which we can then lift up to the eventual political decision making. Contagion analysis is very, very simple, even if it sounds a little bit complicated. We use some tools from MIT, something called the design structure matrix, which is a way to investigate dependency across residue and across flow and across components and across function. And we use something called incidence matrices. And of course, this stuff all links back to the mathematics of residuality theory. And to find out which components are affected by similar forms of stress, where should they be grouped, how should they look? And it looks like this. So incidence matrices, then we run stressors against our flows, we run function dependency graphs, we look for patterns, we do some counting, and we say which functions get hit by a whole lot of stress, which stressors hit a whole lot of functions, and we make boundary decisions about our components using a very, very simple set of rules. And this is traceable. So when you go into an architecture, if you're reviewing an architecture, something that developers have done, and you ask them, how did you make decisions about these component boundaries? Very few teams can give you a concrete example. Usually it's a pattern, usually it's a gut feeling. This takes those patterns, gut feelings, and assumptions, and forces people to discuss them. And it goes very, very quickly. And it's much, much more effective than any of these guru-led methodologies for identifying components, which are all very, very vague and never commit to anything. This can give you some very strange results where you get functions existing in the same component because of their response to uncertainty and complexity. But it's quite simple to learn. Once we've gotten to that point, we now have an architecture, and we have component boundaries, and we have linked up all our flows. What we've actually done is identified what is a process, what isn't the process, where might there be green arrows. Remember, we can't predict them, but we can get a sense that they're there. And what way is stress going to hit this system? So we're in a pretty good position. After that, we get to systems engineering. And systems engineering is important, remember, because in the complexity, we've dealt with the stuff out here in the tails, the stuff that's hard to predict. Now we've got to make sure that we do the job in the middle that we're actually paid to do. And here we learn things like DevOps, failure mode effects analysis, the architecture trade-off and analysis method, different testing strategies, cloud techniques like scale units, telemetry plans, and we merge these ideas with the ideas that we've used from complexity science to get this far. And so what we end up with is a scientific basis for practicing architecture. A completely different set of techniques than what we're used to using today, but there's a scientific basis for what we're doing. And that's a huge step forward for our industry. Residuality theory then allows us to teach and train architects very, very quickly. You don't need to go on a course in TOGAF. You don't need to do an MBA. You don't need to learn every single cloud technology that there is out there down to the API level. Okay, this very, very quickly isolates and identifies what you as an architect working with cloud need to know. And it allows us to learn quickly because we focus on very, very different things. Once you start looking at residue, you don't really care about the API level of components. You care about how a component behaves when it's part of a residue. How can it be broken down? How much of it can survive? Which function can be preserved? And where do you set its boundaries? And so we learn components and functions in a completely different way than we would learn if we weren't adopting this approach to architecture. And this allows us for just really solid cloud architectures that have some chance of surviving in today's world, which is incredibly unpredictable. We can also use residuality theory to analyze and assess other approaches. So once you've learned residuality theory, you can go back to something like TOGAF or SAFE or domain-driven design and say, what's actually happening here? How does this impact residue? And what you'll find is that most methodologies are attempting sometimes very clumsily to preserve residue. Okay, so we've had an idea for the last 60 years that this is what we want to do, but because we haven't engaged with the complexity sciences and because complexity science wasn't mature enough, we don't really have a language or an idea to describe that. This makes it concrete. And so what we're doing together with DFCOA is we were putting together a course on this stuff, and it's 4 very, very intense days. Working with designing a cloud architecture. So every participant in the course brings a problem with them that they have to solve. There's a lot of focus on learning how to learn. There's a lot of focus on critical thinking. And so day 1 of the course, we'll do this introduction, which is an extended version of what you see now, an introduction to the complexity sciences, to the concept of anti-fragility, and to the concept of residuality and residuality theory. On day 2, we'll learn how to learn cloud. And so we'll learn a cloud platform in 1 day. Using the ideas from residuality theory, we'll approach learning in a completely different way. And we'll learn how to learn cloud, which is a very, very different cloud course than anything you'll ever have seen before. Day 3, you'll actually design a cloud system. You'll have learned enough about architecture and enough about cloud to make your first tentative steps towards designing a cloud system. And day 4, we'll spend testing the design, being skeptical about it, asking questions, and we'll look at the politics of this kind of work and how this kind of work evolves over time and how you work with the agile people and TOGAF people and SAFE people and managers and how you get these ideas to work in a complex and crazy enterprise environment. And so residual analysis then, which is the application of residuality theory in software engineering, It replaces the need for any kind of architectural framework. If you have this in your back pocket, this is the foundation of your architectural practice. You cover everything from requirements engineering to risk management to design decisions to component boundaries to project planning. Everything can be covered by residuality theory. And it gives you a key, it gives you a philosophy, it gives you a standing, a way to assess things. It doesn't reject anything, it doesn't ask you to change what you believe. All it asks you to do is to expose what you believe to a residual analysis and still be confident in what you're saying. It's an incredibly tough form of training. Residual analysis makes it very, very easy, I believe, and that's been the purpose of it and the reason I developed these ideas, to take senior developers and junior architects and turn them into performing senior architects. It's very tough, though. It requires real critical thinking, but essentially it's about reinforcing heuristic. So you get faster and faster and faster at this over time. It seems like a lot when it's first explained. There's a lot of ideas, there's a lot going on. It asks you to do something which is deeply uncomfortable, and that is to step outside the STEM educations that many of us have had and to see the world from a broader perspective, and to maybe question some of the assumptions that you've carried with you from your STEM education about the predictability of the universe or the order that exists in the world. To get started, there's a whole bunch of articles which are referenced here. You can try the techniques for yourselves and build from there. There's never any commitment. The ideas are deliberately built so that you don't have to commit to them. You don't have to buy into a religion. The entire process asks you to think critically and to reject anything that you see that isn't working. So I'm not trying to sell you ideas. I'm not trying to start a movement. This is about becoming a better architect, and nobody's path through this is going to be the same as anybody else's. So with that, this is my email address. If you find these ideas interesting, and we haven't really had so much time this morning, we haven't had time to cover absolutely everything. But if you find these ideas interesting, if you follow me on LinkedIn, you'll see a constant flow of articles and ideas connected to these ideas around complexity science and software engineering. And with that, we'll go over to questions. And I have a couple of questions here that have come in. Is cloud just an enabler? Is architecture about limiting the degree of freedom of how to design a solution? Essentially, yes. All software engineering is about limiting the degree of freedom. Every command that you write in a programming language is about limiting the flow of electricity to a processor. And in the world of complexity science, we often describe solutions as a number of constraints. And a constraint is anything that restricts what you can do in the future. And sometimes a constraint can be enabling. And in that sense, cloud is an enabling constraint. It's saying that you can queue messages this way, or this way, but you can't do it this way. But those constraints are not strictly enforced. People can do whatever they want. If you want to choose an entirely wrong component in cloud, you can still do it. The thing that cloud does is that it introduces a whole bunch of new constraints, many of which we aren't aware of, around the boundaries in software systems, and that's because it is service orientation embodied. So I wouldn't say that cloud is just an enabler. I would say it's an expression of architecture, of a number of architectural ideas, which completely changes what's possible for us as we move forward. Another question I've had here is, if organizations are shutting out architects, how do you manage the red arrows? The residuality theory, as we've gone through, is how we manage the red arrows. We don't know what those are going to be. We don't know when they're going to happen, and we don't know exactly what impact they're going to have. So what we do instead is that we produce a system according to the residual analysis, which shows a tendency to be able to respond to stress that it wasn't designed for. And we do that by using the testing set and the training set. And that's the best we can do. Once we show that a system has a tendency to survive things that it wasn't built for, then that's as far in the universe that we live in, according to what's predictable and what's ordered and what's not, that's as far as we can go. And another question about it here is, how do you handle or mitigate accidental architecture? Residuality theory is very, very, very much about avoiding accidental architecture. If you go on the course, you'll see that we focus very much on how you document all of these decisions, how and why you're making them. And so the idea is that architecture will stop being accidental. And that's something that we need to get away from. Another question I have here, why not a movement as an enterprise? So building up a book of knowledge. Well, so when I say movement, and the question comes from Cork, I don't want these ideas to be lifted up in the same way that, for example, Scrum or CF has, where they're presented to executives who don't really understand the ideas with the objective of making money. A movement, yes, it would be great if lots and lots of people adopt these ideas, but I want any movement that comes out of this to be about the people and the way they apply those ideas, not about the way the ideas steer the people. That's what I mean when I say that. So this should very, very much be organic. It should be about the practitioners of these ideas. Every architect that I've ever met comes from a different place. We've all been forged in different fires. We've all had different experiences, different projects, different failures, different successes. And that leads to a very, very interesting group of people with different views on the world and different views on what works and what doesn't work. And so every architect will absorb these ideas in a different way because we've all been formed differently, and we'll apply them in a different way. When I say I don't want the movement, I don't want rigidity. I don't want to stop that personal development that each and every one of us has the capacity to engage in when they engage with these ideas. And movements bring rigidity, and I don't ever want to see people on internet forums arguing about what's a residue and what's not a residue. These are very, very personal things that we develop as skills over time. Hopefully that's an answer to your question. Any other questions? We have 3 minutes left. If anyone has any other questions, if you have any questions that you don't feel brave enough to ask, you can email me on this address in English or Swedish. I do respond pretty quickly to questions, so don't be afraid to do that. And if there's no more questions, then thank you everyone for taking the time and listening here today. The next course is on the 17th of May, which is going to be virtual, and it'll go through all the things that we've talked about today. And maybe I'll see some of you in the future on the courses, either virtually or in person. So with that, I'll hand back over to Max.
Ja, då får vi tacka allihopa för idag och hoppas att det har varit spännande. Om det är någon som har någon fråga som dyker upp om själva en kursbokning till exempel, så slå gärna mig en signal eller skicka ett mejl. Jag lägger ut mina upp i chatten nu om det är någon som har någonting. Och det var väl egentligen det då, tycker jag. Vad säger ni? Ska vi ta en runda av här?
Jag har inget mer idag. Som sagt, om ni har frågor, det är bara att mejla. Följa på LinkedIn och ställa frågorna där offentligt om man vill. Och vi hörs. Och trevlig helg!